So now we're talking about differential scanning calorimetry, or DSC, okay? It's a method to study changes. It's using heat change to look at some different biochemical reactions or transformations. It's sort of our most direct method to study energetics, particularly if, say, a conformational change in a molecule. So moving from a lower energy state like trans, how much energy or how much heat do I have to put in to get it into the cis conformation? If I want to unfold a protein from folded and break all of the non-covalent interactions and H bonds holding it, how much energy does that take? So this is a great way to study it. Okay. ITC, or isothermal titration calorimetry from last time, basically sort of asks how much heat has to go in or out to keep the temperature the same. Okay, DSC is a little bit different. It's saying as I put the same amount of heat into the cells, what's the difference in temperature? Right? So rather than keep the temps identical and see what I have to do with heat in order to keep that happening, such as I dripped in my ligand or whatever. Okay. DSC, I still have the sample of interest, so I still have probably water with my proteins inside. And then my reference cell's just my water, right? So I can subtract that out and see what was going on just with proteins. And I put heat in. I'm putting in heat, Q, into the reference cell, and I'm putting in heat into the sample cell. And I'm looking at, what's the difference in temperature, what's going on between these two. So my system is I have my buffer, water typically, and then I have buffer plus probably a protein. I don't know why this became a problem before, but the cell is the name for this vessel here. It's not like a cell in your body. I don't know how that was confusing in the past, but it has been. Okay, so this vessel is isolated from each other. They're open to the atmosphere at the top, okay, so that we can keep pressure constant at atmospheric pressure, okay? So that this is, if we're at this sort of essentially isobaric case, we can talk about enthalpy, right? We only talk about enthalpy at isobaric, okay? Heat the cells both really slowly, also do some temperature scanning slowly so that we can keep the systems near to equilibrium. Quasi-adiabatic is meaning that all of the heat is going in to these two vessels. We're not worried about, this is insulated here, so we're not really worried about heat being lost to the surroundings, not significantly so. Okay. And since the two cells are going to have different heat capacities, the reference cell, it's just the heat capacity of my water, or my buffer, whatever it might be, as I start putting in heat here, to raise the temperature, eventually it's going to look different because I have some proteins going on in here that have potential energy modes. Okay, they're going to require different amounts of heat to get the same change in temperature. So again, this is just another visual. What is the plot of heat capacity versus temperature? So I'm asking you for T, CP. What does that plot look like for an ideal gas? Someone describe it to me. Or use your hand motion. Yeah. You think it looks like what? This? Anyone else have other guesses? This one? Was that what I got? For an ideal gas, this is a flat line. It's a constant. It's not changing. Okay? It continues to take the same amount of heat to raise it 1 degree every time. Okay? How about for water? What does that look like? If I'm just heating water. It's a flat line. It's higher now. This was 70 some joules per mole Kelvin, right? This was like 20. Scale's messed up. It's a constant. Now, when we talk about, we have, for water, it's just going to look like a flat line. Heat capacity isn't really changing as I raise the temp. Same amount of heat, takes it 1 degree every time. when I have some biological molecules in there, in my solution, it looks something like this, okay? Here's heat capacity on my y-axis, here's temperature, okay? So this is pretty flat. All that's really happening as I'm putting in heat now is I'm raising the temperature and I'm just increasing the kinetic energy of the whole system. Everything's moving faster, temp is going up. This is mostly just dependent on the heat capacity of the buffer, okay? And eventually, I reach a point where I'm putting in enough heat that rather than just raising the kinetic energy and raising the temp, I actually start unfolding my proteins, okay? So it takes more heat, remember this is heat per temp change, it takes me a lot more to get even one more degree of change, because rather than raising the temp, I start unfolding the protein instead, okay? And so I get this peak here, we call this middle point, okay, the center of our DSC curve, the melting temp. This is not melting temp like a phase transition, okay? We're not melting the protein in a way that like suddenly it's no longer solid protein amino acids, okay? It simply means we're going from folded, nice and neat, to unfolded, and we treat this like a perfect transition, okay? It's either folded on one side, it's unfolded on the other. It's not partially unfolding, okay? Just a two-state situation. Energy required to disrupt non-covalent interactions in a folded macromolecule will result in a change, or, well, in this case, an increase in heat capacity.